Hello everyone, I'm Qing Deng. Today in this video, I'm going to present my machine learning project, a model that could predict vehicle destination. Before we get started, I'm going to give you some background information. With the increasing global urbanization, it's important to upgrade transportation by alleviating congestions. We're here to help by predicting the destination, whether a vehicle will be in or outside of the city center, given the previous location and the last enter point. The dataset looks like this. Here you can see 11 features in total. 6 of them are used in the model. They're the user hash number, trajectory ID, and 3 entry and 3 exit pieces of information. One thing to notice is that each user could have different number of trajectories, maybe 1, maybe 10. With this information, we can plot the vehicle traces like this. So here is the 4 pieces of trajectories of one user. The data set is a little bit messy when I first got them, so I clean and organize them by the following steps. The first step is to get rid of the unnecessary data. The data with the same enter and exit time are considered not helpful to the model. Then I normalize the data. Then I label the data with 1 or 0 manually to indicate whether the destination is in or out of the city center. Lastly, I group them by the user hash number in order to compile them into a sequence and then feed into the LSTM model. Here is what looks like before and after processing. You can see in the after processing part, all the data are skewed between -1 and 1. Why to choose long short-term memory models instead of deep neural network models? First, since we have variable sequence lengths, it's not possible to feed them into a deep neural network, which requires a fixed length of input features. Second, vehicles are likely to have moving trend. Thus, a better memory is required to keep track of what happened before and apply it to the future. Here is the model on the first try, which has a clean LSTM structure. However, there's a dimension mismatch problem. We can see that the dimension for the trajectory 0, 1, and 2 are identically 6. However, you can imagine in a real life situation, we do not have the exit part information because we're supposed to predict this exit part. Since the last input is lack of 3 exit features and only have a dimension of 3, apparently a pure LSTM model can no longer solve the problem. So we move on by adding another fully kinetic layer at the end. Suppose a user has a length of trajectory of 6. For the first 5 inputs, they're fed into the model the same as before. However, for the last time step, here comes the improvement. We first extract the hidden unit H4, then collaborate it with the 3 features of the last entry point. Then, this combined vector, which contains both the memory of the previous path and the last entry data point information, is the input of the fully kinetic layer. Hopefully, this could lead to a correct future prediction, which is whether the object will be in or out of the city center, labeled as 1 or 0. Here is the performance of how is the performance of the revised model? The accuracy is roughly about 83%, since the labels are relatively balanced in each class. So using the accuracy to measure the model performance makes sense. The model is trained with Atom Optimizer, which is capable of minimizing the training loss by a lot. However, SGD Optimizer is also well known and widely used by industry. Thus, I tried a combination of these 2 optimizers. As you can see in the image, The sudden jump occurred at iteration of 100 is caused by the change of optimizer. Even though the training loss keep decreasing and reached a fairly low value, the accuracy is not even as good as before. However, I think this should work, but needs more patience and time to figure out the better hyperparameter. To be honest, I'm not very happy with the accuracy, so I tried a different way to calculate the loss function. Originally, I think of this problem as a binary classification problem and use cross-entropy loss. Later, I changed the way of thinking this problem and want the model to predict the destination coordinates instead, and use the mean squared error to calculate the loss. This loss function did give me a lower training loss, but the validation said accuracy is worse. I think it's because of the under-organized data and the overfitting problem. However, in order to learn more from the mistakes, here I plotted the trajectory of the wrong prediction by the model. The pink dashed box is the city center. These plotted vehicles landed at the city center eventually, but while the model tells us the opposite. After inspection, here are two observations. First is the existence of the outlier, like the purple and green lines. All of their previous trajectories and not only go back and forth a lot, but also far away from city center. I think their existence have a huge impact on the model result. Second is about the two short distance trajectories. If we zoom in the area of the red and blue trajectory, we could see these very tiny short and not smooth lines. I think it is this data that adds noise to the training process. If I have more time, I will improve these two aspects. First is to visualize the data before feeding them into models, because it's important to have a sense of how the data look like, and the machine will learn better from reasonable data. The second and third point come from the error inspection. Extreme length and sharp trajectories, as well as the outlier, will ruin the model performance. For the model itself, I would like to add p-hole connections so that the later cells may not only depend on the previous activation value and the current input, but also the memory cells. I hope this variant of LSTM will improve the learning process. Last but not least, training longer and tuning hyperparameters will always improve the performance. So, this is my project, Predicting Destination. Hope you like it, and thank you for listening.